All right, this is Unit 1, Lesson 14 of our calculus class. The unit is Limits and Continuity. The Lesson 14, the last lesson of this unit, is called Working with the Intermediate Value Theorem. So what we're going to learn in this lesson is, like the name suggests, what is the Intermediate Value Theorem? And it is not named after Dr. Intermediate Value. Like most theorems in calculus, this is named after the theorem's named after what it does, finds the intermediate value of something. And brownie points if you can guess who this is a picture of by the time this video is over. So, intermediate value theorem. So if f is a continuous function on a closed interval a to b, and d is a real number between f of a and f of b, then the intermediate value theorem guarantees that there's at least one number c between a and b such that f of c equals d. So that's the theorem. Let's break it down. First, f is a continuous function on the closed interval a to b. So from a to b, this function starts at a, and it's going to go all the way to b because it's continuous. It could go straight there as a straight line. It could be kind of wavy. It can go really up and then down and then up and down. And then no matter what, though, a will eventually make its way to b. And f of a will eventually make its way to f of b on our range. So the second part, d is a real number between f of a and f of b. So if I have f of a here and f of b is up here, somewhere between f of a and f of b, there's some value of d. And so the third part, there's at least one number c between a and b such that we can find f of that c, and it'll equal to d, this value here. And that is the formal way. If you think about it, to get from a to b, at some point you have to cross d, right? So that's kind of what this theorem is saying. Take a moment and just like process that, because once you get it, it's like, oh, okay, that's all it's saying. Yes, that's all it's saying. So to get from a to b, we have to cross c, and to get from f of a to f of b, we have to cross some point d, such that f of c would equal that d. All right, let's look at an example here. So we're basically going to use our 3 steps of our definition for the intermediate value theorem to check this thing. We'll just go step by step. So let h be a function defined as such. Can the intermediate value theorem be applied to guarantee a value in the interval 1 to 5 where h of x equals 0? Justify our answer. So step 1, is f continuous over the interval 1 to 5? Well, we have a polynomial function, and polynomial functions we know are continuous over all real numbers. So yes, it will be continuous on the interval 1 to 5, or any interval for that matter. So the next part, d is a real number between f of a and f of b. Okay, so if we look at h of x equals 0, a would be our 1, b would be our 5, and then 0 would be our d value. And so is there f of 2, f of 3, f of 4, some number, the f of that number between 1 and 5 will equal 0? Well, we could find out. If we plug in f of 1, we could do some algebra, and we'll find that f of 1 equals negative 10, which is below 0. If we plug in f of 5, the other end of the interval, 1 and 5 are interval numbers. If we plug in f of 5, we can do some math and find that f of 5 is equal to 50. And so if we map f of a to f of b, we would get negative 10 to 50. Well, 0, our d value, is in between negative 10 and 50. So to go from 1 to 5, we have to, at some point, if we go up from negative 10, at some point we have to cross 0 on our way up to 50. So yes, the intermediate value theorem works for step 2. So then therefore we can conclude, because it's continuous from 1 to 5, and because our h of 1 is less than 0 and our h of 5 is greater than 0, that there must be some value c between a and b such that h of some number c is equal to 0. All right, we can confirm this with our graph. So if I look at values x equals 1 to x equals 5, I can see our interval. And at 1, we have, here's our negative 10. And then at 5, it's way up here at 50. We can see 50 right there. And for our line to go from negative 10 up to 50, at some point we have to cross 0. So that's right here. We see a value. So our c value would be 3.533. So yes, there is some value c such that f of c equals 0, or h of c equals 0. That c value is 3.533. All right, so here's a trig example. Of course, trig example. So g of x is going to be our function. It's defined as tangent of x, which we know to be equal to sine of x over cosine of x. Can the intermediate value theorem be applied? So if we look at our interval from 0 to pi, is there, are we guaranteed that there's some g of x where it's equal to 1/2? Step 1 is f is continuous over the function 0 to pi. And if we know a thing or two about the graph of tangent, we know that this is not continuous from 0 to pi. We know that, in fact, we have a vertical asymptote at pi over 2. So because we do not meet the criteria number 1, we are not continuous on the interval 0 to pi, we cannot apply the intermediate value theorem. So there, to be clear, there may be some value c where g of c equals 1/2, but the intermediate value theorem cannot be used to guarantee that there's a value. We can check that graphically too here. Here's our interval from 0 to pi, and you can see there's our vertical asymptote right in the middle, which we know to be at pi over 2. And we could get a value of, there are some values of c such that it equals 1/2. In fact, I think there's 2, no, just 1. The value is right here, so it does exist. That point is 0.464. We just can't use the intermediate value theorem to prove that it exists. So takeaways, intermediate value theorem, it exists, it's a thing, and we have a 3-step criteria for using that theorem. And most theorems are in fact named after what they do, not who invented them. So if you recall, let's go back to that picture here. Who is that guy? Archimedes? I can't remember anymore.